Good day and welcome to the second presentation of Elements of Neural Network and Deep Learning. I am Tiniam Ganesh. This course, like my other sessions, is going to be based on two courses I did from Coursera, namely Neural Networks and Deep Learning by Professor Andrew Ng and Neural Networks and Machine Learning by Professor Jeffrey Hinton, and also from two books, Neural Networks and Deep Learning by Michael Nielsen and Deep Learning book by Ian Goodfellow, Yoshua Bengio and Aaron Corwell, and other material from the internet. In the last session, I had shown how in a neural network, if we change the value of the weights in the neural network, in the toy example, that is by delta W, there is a corresponding change in the output by delta output. And this corresponding change in the delta output means that there is a corresponding change in the error. So hence a small change in the weight in the weights will result in a corresponding change in the output and a corresponding change in the error. And the intention of our neural network is to be able to minimize the error for all possible training data sets. So we need to come with a set of weights for a set of weights in the input layer and all subsequent layers, such that our error is the lowest for all the samples in our training data set and also subsequently in the test data set. And this is done by a process known as gradient descent in neural network, which you've already seen in machine learning. The only difference is in neural networks there is a cycle of forward propagation and a corresponding cycle of backward propagation in each cycle of gradient descent, which helps us to minimize the overall cost or reduce the total error. We will see how this is done as we move through in the next couple of slides. I would like to first take logistic regression as a two-layer neural network. So what is logistic regression? Logistic regression is typically used in scenarios where we have a set of features and the target variable or the output is one of two possible outputs. So for example, if you have a tissue, it can either be cancerous or benign, or in the case of email, the email is either a spam or not spam. So essentially, logistic regression, the output variable is one of two distinct classes, and that is where we use logistic regression. And logistic regression is basically a supervised learning algorithm. That is, we have the data set is labeled. That is, we have already a data set where for every set of inputs we know the corresponding output, which is either a 0 or a 1. And the goal of logistic regression is to minimize the error between its predictions and the actual data. So for example, if we had a set of features x1, x2 up to xi, then we can take the weighted sum of these features plus some bias and and compute an activation function. Let's say it's z, and we can rewrite this as z is equal to w transpose of x plus b, where w is this column vector w1, w2 and w3, and x is our input features. So this is just a matrix multiplication. So z is equal to w transpose x plus b. But since we know the output is one of two possible values, how do we manipulate this function such that our estimated output is one of two possible values? And this we can do. There's a convenient mathematical function known as a sigmoid function, which we use. So basically, we pass this linear activation into the sigmoid function to give us our estimated output, which is either a 0 or 1. Now let us take a closer look at the sigmoid function. So we have our linear activation, which is a weighted sum of the features plus a bias. That is, z is equal to, if you had two features, it's w1 x1 plus w2 x2 plus b. And the sigmoid function is defined as 1 over 1 plus e power minus z. And you can see its behavior here. So the sigmoid function at the value of 0, it has a value of 0.5. And for small values of increasing values of z, the sigmoid function increases. And for large values of z, it actually plateaus to 1. Similarly, for small values of z, it decreases, and for large negative values, it actually plateaus at 0. So let us see how this works. If z is large, then the sigmoid function, which is 1 divided by 1 plus e power minus z, If z is large, it is 1 by 1 plus e power of a minus of a large number, which will be which will be close to 0. So it will become 1 over 1 plus 0, which is 1. And if z is very small or negative, then it becomes 1 over 1 plus e power of a minus of a negative number, which will be a large positive number, which will be 1 over 1 plus infinity, which will be 0. So essentially, you can see that the sigmoid function for large values of z, it plateaus at 1, and for large negative values, it actually plateaus at 0. So hence the sigmoid function essentially takes one of two values, which is either 0 or 1. And for this intermediate range, which is where it is where it slowly increases or slowly decreases, and not exactly 0 or 1, in our code we actually say if it is greater than 0.5, it is the sigmoid function output is 1, and if it is less than 0.5, we say the output is 0. So let us consider logistic regression as a two-layer neural network. So assuming we have two input features x1 and x2 and a bias, we choose a set of weights w1 and w2 and a bias, and we compute the linear equation z is equal to w1x1 plus w1x1 plus w2x2 plus b. So we have the linear equation, and then we pass it through the sigmoid function to give us an estimated output, which is either very close to 0 or very close to 1. Now we need to determine how well, assuming that we are able to model our network using this simple two-layer neural network. Now we need to be able to determine how well our neural network performs. In the case of logistic regression, we have what is known as the loss. This loss actually captures how well our logistic regression model actually performs on any given data set, and is given as L of a comma y, where a is the estimated output and y is the real output, is equal to minus y log a minus 1 minus y log of 1 minus a. So as I said, a is the estimated output and y is the actual output. Now why do we choose this loss function? It is also called the logistic loss. We can see this loss function. So here the loss function, if we take the linear equation z is equal to w transpose x plus b, then our estimated value of y, if you pass this linear equation function through a sigmoid, which will give us a value either very close to 0 or 1, so we pass it through a sigma of w transpose x plus b, where sigma, that is sigmoid function, is given by 1 plus e power minus z. Here y hat is our estimated value and y is the actual value. And what do we want? We want our estimated value y hat to be as close to our actual value. If our estimated value, that our model is able to estimate y hat, and this y hat is very close to our actual y, then we can say that our model is performing well. Now the logistic loss, as we seen in the previous page, is given by L of y hat comma y is equal to minus y log of y hat plus 1 minus y log of 1 minus y hat. Here I just replace a with y hat. Both are one and the same. Now let us see why this log loss actually works. Now if y is equal to 1 in this equation, we can see this second term becomes 0. So hence we will be left with L is equal to 1 minus of 1 into log of y hat. Now if y hat is very close to 1, then we can see that this loss is essentially 0 because we are essentially taking the log of 1, because y hat is close to 1, log of 1, which will be 0, we know it's 0. And alternatively, if y hat, instead of being close to 1, it was close to 0, then if we take the log of 0, it will be equal to infinity. So what it's saying is, if y is equal to 1 and our y hat is also close to 1, then our loss, which also means the error, is actually close to 0. Alternatively, if y is equal to 0, then we can see this first term actually goes away, then we are left only with the second term, which will reduce to minus of log of 1 minus y hat. Now we can see if y hat is close to 0, then we are left with minus log of 1 here, and which will be very close to 0 because log of 1 is 0. Alternatively, in this form, in this equation, if you had put if y hat was close to 1, then it would be minus log of 1 minus 1, which would be 0, which will essentially come to infinity. So what does this say? It says if our estimated value of y hat is close to y, then our loss is 0 or our error is close to 0. Alternatively, if it is If it is if it is the other way around, then our loss is infinity. That is, if y is equal to 1 and y hat is close to 1, our loss is 0, and if y is equal to 0 and y hat is close to 0, then our loss is 0. So hence this log loss is used in binary classification to determine how well our model performs. Then we come with something called the cost function. The loss function is essentially the error with respect to one training sample, but we need to find how our model performs with respect to all the training samples. So hence we take the average of the loss, that is 1 by m, the sum of the loss over all the training samples, so which is denoted by j of wb. It is a cost function, and our objective or goal in our neural network is to be able to minimize this cost and get the set of weights which will result in the lowest cost for all the training samples. And this is done through a process known as gradient descent. So here we take a simple example, assuming we have weights and we have the cost for the different values of the weights. This is actually a parabola, and one of the other reasons why the logistic loss function shown here is used is because it has a convex ball shape and it's very easy to find the minima. So if we had a curve like this, if it was a simple curve, then we could simply take, we know in calculus that if we take the derivative of a function and we equate it to 0, then we know the point where its derivative is equal to 0 is the point where we get is the local minima. But in the case of machine learning, we cannot solve this equation in this way, but we have to follow this process iteratively. And the way it is done is, we take any point on this curve, and at that point we find this slope. So for example, if we take this slope of this curve at this point, it will be positive. That is the slope, or dj by dw, will be positive. So the weight, what I do is, this is an iteration, so weight I is weight I minus alpha into the slope, which is dj by dw, and at this point it will be positive. So w minus alpha into a small positive number will be small positive number. So essentially from the current value of wi, I subtract a small positive number, which will be a value which will be less than its previous value. So I will move in this direction from the right to the left. Alternatively, if I had started from on this side of the curve, the slope would be negative, that is dj by dw would be negative. So here I would be from wi, the current value, I would be subtracting minus alpha of a negative number, which will be positive. So the new wi would be wi plus a positive number, which will be a larger value. So I will move from left to right. So regardless of where I start on this curve, I will eventually arrive at this minima. So in gradient descent, I will iteratively find the weights and the bias by moving along this curve, and finally come to the point where I get the lowest cost, and that will be the set of weights which will actually which I will have to use for my model. So in gradient descent, the process basically that is followed is, we start with an initial set of random weights wi, bi. We go through a cycle of forward propagation, and then we compute the cost, or compute the loss, and then in the backward propagation we compute the gradients, that is dj by dw, and find the new set of weights wi and the new set of bias, and we get a new set of bias, and then we again do this forward propagation and backward propagation. We forward propagation, compute the loss, and then we do this backward propagation. Let us go through this process a little bit more slowly to understand how we go about this. So the goal of neural network is to identify the set of weights and biases for all layers, such that this combination of weights and bias for our neural network will result in the lowest cost for our neural network when we apply for any of the training samples. So for logistic loss, let us take two features, x1 and x2, and the corresponding weights w1 and w2, and a bias. So we can compute the linear equation z is equal to w1 x1 plus w2 x2 plus b. Then we compute the we pass this linear equation through a sigmoid function and compute a is equal to sigma of z. Now we need to determine how well this model performs, and for that we use this logistic loss function, which is L of a y is equal to minus y log a minus 1 minus y log of 1 minus a, and this is one cycle of the forward propagation. Now, as I said, our objective is to somehow find how the cost varies with respect to the weights and the bias, so that we can use it in our gradient descent formula to arrive at the minima or the lowest cost for our neural network. So that is what we need to do. So we can see that z is a function of the input features, and a is a function of z, and to get and then the loss is a function of a. To get at how the loss varies with respect to the weights, we have to find the derivatives of the loss with respect to the activation function, and then the activation function with respect to z, and then we have to go in the backward direction. We will just see this. So since the loss is given as L of a, the loss of ay is equal to minus y log a minus 1 minus y log of 1 minus a. If I take the derivative of this, you will get dl by dA is equal to minus of y by a plus 1 minus y log of minus of that is minus of 1 minus y, the derivative d by dA of log of 1 minus a, which is will become plus of 1 minus y divided by 1 minus a. That is, since d by dx of log x is equal to 1 by x. Now here are some key results. The derivative of sigmoid. How do we find the derivative of sigmoid? We know the chain rule. If y is equal to f of u and u is equal to g of x, then dy by dx is equal to dy by du into du by dx. You can see that. Now let us find the derivative of sigmoid. The sigmoid of z is given by 1 plus e power minus z. Now let us assume x is equal to 1 plus e power minus z. So I can rewrite this equation as sigma of z is equal to 1 by x. Now d sigma by dx is equal to, if I take the derivative of this, it becomes minus of 1 by x squared, and I substitute for x as 1 plus e power minus z, it becomes minus of 1 by 1 plus e power z the whole square. Now I take the derivative of this dou x by dou z. This is a constant, so I will be left with minus of e power minus z. Now using chain rule, we have dou sigma by dou z is equal to dou sigma by dou x, which is this, and dou x by dou z. So I'll essentially need to multiply minus of 1 by 1 plus e power minus z the whole square into minus of e power z. Now I rewrite this as e power minus z divided by 1 plus e, if I just simplify this, e power minus z divided by 1 plus e power minus z the whole square. Now I'll rewrite this as 1 by 1 plus e power minus z into 1 minus 1 plus e power minus z, which is the same as this. But since 1 plus e power minus z is equal to sigma, I can rewrite this whole equation as sigma into 1 minus sigma. So hence the derivative of the sigmoid sigma by dou z is essentially sigma into 1 minus sigma. This is what this thing proves. Now let us come back to this equation. The backward propagation, we have seen dou L by dou A. Now we need to find dou L by dou Z, which is equal to, using the chain rule, it is dou L by dou A into dou A by dou Z. We have already seen dl by dA is minus y by a plus 1 minus y into divided by 1 minus a, and dA by dz is the derivative of sigmoid, which you have seen here, sigma into 1 minus sigma. So here sigma is actually a, so dA by dz is a into 1 minus a. Hence dl by dz is equal to, I need to multiply this term into the second term, a into 1 minus a. If I multiply and reduce this, I will finally get dl by dz is equal to a minus y. Now here we come to the last and final step. As I said, the objective of gradient descent in neural networks is to find how the loss or the cost varies with respect to the weights in the layers. Okay, so that is what we are going to do now, and that is one of the reasons why we are trying to find the derivatives of dl by dA and dA by dz. So now we come to the last and final part. dl by dw1 is equal to, using the chain rule, it is dl by dA into dA by dz into dz by dw1. Now dl by dz, that is dl by dz, this whole term is a minus y. Hence dl by dw1 is equal to, basically I just rewrite this whole thing this way, dz by dw1, I write it here, and this whole term becomes dl by dz. So dz by dw1, dz by dw1, if I take the derivative of this, these two terms become constant, so I'll be left with x1, and derivative of dl by dz is a minus y. We saw that here. Dl by dz is a minus y. So it is x1 into a minus y, and dl by dw2 is dz by dw2 into dl by dz, and dz by dw2 is, this becomes constant, so it will be basically x2 into dl by dz, and dl by dz is a minus y, so it is x2 into a minus y, and dl by db is equal to dz by db into dl by dz, and dz by db, these two become constant, so it becomes db by db, which is 1, so it's 1 into dl by dz, which is a minus y. So these are the three terms. So we found how the loss varies with respect to the weights and the bias, and now we can use it in our gradient descent formula. So in the forward propagation cycle, we start with some random values of weights when we start the neural network, and then we do a cycle of forward propagation. That is, we do this, we compute the linear activation, we compute the sigmoid, we compute the loss, and then we compute the cost. Then we compute the cost, and then we do a cycle of backward propagation, and we compute how the loss varies with respect to the weights and bias. That is, how the cost, not the loss. We have to find the average of the cost over m training examples, and then we iterate. From the value of the initial weights, we subtract alpha dj by dw, where dj by dw is how the cost varies with respect to the weights w1 and w2, and dj wb by db is how the cost varies with respect to the bias. So from the current weight, we substitute minus alpha into how the loss with respect to the weights and the loss with respect to the bias, and get the new set of weights. And with these new set of weights, we do a forward propagation, compute the cost, do a backward propagation, compute the gradients, compute the new weights and bias, and keep going through this cycle iteratively till we get to the lowest cost. And when we get the lowest cost, that is the point, and that is the set of weights which we use in our neural network on any new training example. So here I have plotted and I have shown. Here you can see the gradient descent. When I start the neural network, it starts with the high cost, and this green is when I used a learning rate. You have to change this learning rate to alpha. When I use the learning rate to alpha, you can see and I do gradient descent, the cost keeps decreasing as I iterate, and then after a point it actually plateaus here. It doesn't decrease any further. So I choose another learning rate, let's say 1.2, and again compute the weights and the corresponding cost, and I plot it. At 9,000 iterations, I see it drops to around somewhere around 0.37, and then when I choose 0.5 as my learning rate, again I do gradient descent. I see, you can see that it gives me a very low cost. Now the set of weights I have arrived by performing after 9,000 iterations, the set of weights and bias is the weights I will use to apply on a new data set, the test set, and my neural network should perform well as long as the training data set and the test data set come from the same distribution. So that is basically how we model a neural network for a simple logistic regression case. And the whole reason why we computed all these equations was because these equations which we have for the backward propagation and the forward propagation can be actually implemented very easily using Python, R, or Octave. So these are all in matrix form. Z is equal to W transpose X plus B, and A is sigma of Z, where Z is a vector. Then we compute the cost, which is the average of this logistic loss, and we compute the weights using this matrix, which is 1 by M into the input features into the estimated output versus the real output transpose, and dl by db is this formula, and we apply gradient descent repeatedly. So all the set of equations which we actually derived can be easily implemented in a matrix form, and hence we can actually solve our neural network and get the set of weights which will perform well. And here's a simple computational graph of the same, which is another interesting way we can see how this chain rule works. So you start from here and go here. So dou L by dou A is the derivative of the loss with respect to A. We have already seen this value, minus y by A plus 1 minus y divided by 1 minus A, and dA by dz is equal to A into 1 minus A. If you do this, we have seen this. Now if I wanted dou L by dou Z, then I just need to take the output of this and multiply with the output of this. I will get A minus Y. Similarly, dz by dwi and dz by db, if for these two I will get this. But now if I want dl by dwi, I will just need to multiply this with this and I will get the corresponding values and equations which I will use for my I will get the dl by dwi and dl by db. And here's how it performs if we use a simple two-layer network. There is just an input layer and output layer. Here I created a set of random test data set with a set of so you can see, let us assume the blacks are the zeros and the yellows are the ones, and I apply this two-layer neural network. This is how it performs. It doesn't do a good clean separation, and that is because we're just trying to implement logistic regression as a neural network, and there are no hidden layers. So this is how it performs. Thank you. So this ends the second in the series of neural networks and deep learning. Thanks for listening.